Today I'm working on an iPhone 16 Pro Max for data recovery. The iPhone does not power on and does not boot. I'm powering the motherboard with an external power supply to check the current draw. A healthy board pulls a small, predictable amount of current when you apply voltage. Right now I'm using the thermal camera to look for any abnormalities or hotspots. I don't really see anything out of the ordinary just yet. It could also be difficult to see anything with the shield still on the board and the sandwich not split. Most often, issues are located on the inside layers of the motherboard. I'm preparing the motherboard for splitting the sandwich. I have to remove everything that might get in the way or melt during the process. On these stacked boards, the two halves are joined by a ring of tiny solder balls around the edge. I'm not using a preheater this time. It's fine to do it like this in this case. The only thing to keep in mind is to not rush it. Go slow and use a low temperature. Too much heat here can warp the board or overheat underfiled chips on the opposite side. And it's done. It took only a few minutes. Now, an initial visual inspection to look for anything that stands out. I'm checking for corrosion, liquid damage, or any components that look burnt or cracked. doing some basic measurements with a multimeter. I'm checking the main power rails for dead shorts to ground, which would point me toward a failed chip. I didn't find anything obvious, so I'm preparing both logic boards for use in a test jig. The second board is a known good donor, which lets me compare readings side by side. This is a Qianli iPhone 16 series testing jig. It allows for fully powering on the motherboard when the sandwich is split. No need to desolder it every time to check if it's working. I connect the power supply only. Checking the motherboard under the thermal camera again. I found something that's warming up. That's a clear sign of a defective chip or a shorted power line. Doing additional measurements near the charging ICs. Right now, I'm checking the board view to know exactly what I'm looking at. I realized that the faulty chip I was looking for is located under the shield. Removing the shield should be done very carefully. Excessive heat can create a lot of problems, much more serious than a defective charging IC. This is a donor motherboard. I'm taking the chip I'm going to use on the customer's motherboard. Since this is a donor, I don't really care about using too much heat. I just need the chip to come off nice and clean. This is the motherboard I need to fix, so I'll be extra careful when removing the defective chip. First, I'm making sure I have enough space to access and lift the chip. I'm using a soldering iron to remove nearby passive components. There's no reason to use the hot air yet. Time to remove the chip now. I'm using higher than usual heat and very lightly prying on the chip with tweezers. This technique helps avoid overheating the whole board, and I'm careful enough not to rip any pads under the chip. Now to clean up the area and prepare it for the new chip. It's rather annoying to put back the passive components using only the soldering iron. But this is better than dealing with the consequences of overheating the PCB. I'm using a special flux cleaning solvent. It works much better than the standard 99% IPA. I'm lightly scraping the oxidized pads to make sure the chip will sit down properly. Reballing the chip is easy. I just need to be gentle with it. It's a very tiny and delicate component. Reballing means applying fresh, evenly sized solder balls to the chip so it can be soldered back down. I'm drying the solder paste a little bit before applying it. Making sure the area is clean and that the chip sits in the correct orientation. Orientation matters because the pads are not symmetrical. Placing it the wrong way would short things out. The chip's position was just very slightly misaligned, but that's perfectly fine. The surface tension of the melted solder pulls the chip right where it's supposed to be. Lightly pushing the corner of the chip to make sure the solder ball is melted and it sits properly. Time to put both PCBs in the testing jig and see if there are any signs of life. This iPhone model won't boot fully without the original charging port and the battery connected. Now I'm using a USB-C power meter to observe the voltage and current draw. Using tweezers to trigger the power on button signal. The phone works and all of the data is saved.